In this video, we're going to take a look at different ways that we can work with Maclaurin series. In particular, we're going to take Maclaurin series for functions such as e to the x and sine x and use them to produce Maclaurin series for related functions, as well as answer questions about the integrals and derivatives of those functions. Four of the most commonly used Maclaurin series are shown here, along with their intervals of convergence. The function 1 over 1 minus x has the Maclaurin series n equals 0 to infinity of x to the n, which converges between -1 and 1, not including either of the endpoints. E to the x is equal to the series from n equals 0 to infinity of x to the n over n factorial. Sine of x is equal to the sum from n equals 0 to infinity of -1 to the n, x to the 2n plus 1, all over 2n plus 1 factorial. And cosine x is equal to the sum from n equals 0 to infinity of -1 to the n, x to the 2n, all over 2n factorial. The Maclaurin series for e to the x sine of x and cosine of x are all converging on -infinity to infinity, and so they converge for all real numbers x. For our first example, we want to find the Maclaurin series for the function f of x equals 2x to the fifth times e to the x squared. We then want to use this Maclaurin series to find the exact values of the seventh derivative of f evaluated at 0 and the eighth derivative of f evaluated at 0. To find the Maclaurin series for f, we're going to start with the Maclaurin series for e to the x, which is one of the commonly known Maclaurin series. We're then going to use algebraic manipulations to build a Maclaurin series for f step by step. So, since the base function here is our function e to the x, we'll start with the Maclaurin series for e to the x, which is n equals 0 to infinity, x to the n over n factorial. We're going to also write out several terms of this just to see how it plays out as terms as well. So here we'd have 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and continue as far as we like, but we'll stop at that point. So there is our function for our Maclaurin series for e to the x. The next step here is to build one for e to the x squared, and we can do that by simply substituting x squared in for x in our Maclaurin series. And so here we're going to have n equals 0 to infinity of x squared to the nth power all over n factorial. So here we're just simply replacing the x in the numerator of our series term with an x squared. And of course, we can use exponents to simplify that a bit. The numerator will now be x to the 2n, still over n factorial. So our new Maclaurin series here will be the sum from n equals 0 to infinity of x to the 2n over n factorial. And if we wanted to write out some terms for this series, we can do that as well. We're going to get 1 plus x squared plus x to the 4th over 2 factorial plus x to the 6th over 3 factorial, and so on. And we can get these terms either by substituting them into the Maclaurin series formula, the x to the 2n over n factorial for values of n equals 0, 1, 2, and 3, or we can substitute them into our terms in our Maclaurin series for e to the x, and replacing x with x squared in each term. And either way will give us this exact same Maclaurin series in the end. Our next step is to multiply this new Maclaurin series for e to the x squared by 2x to the fifth, which is a constant and a power of our variable x. So picking up from our Maclaurin series for e to the x squared, we now find f of x by multiplying that by 2x to the fifth. For our power series, we're going to end up multiplying the entire series by 2x to the fifth. And because this is just a power series, we have algebraic rules for how to handle this. The 2 simply comes inside our summation, and so we're going to have just a factor of 2 now in each term. And when we combine x to the fifth and x to the 2n, we combine our exponents, and we get an x to the 2n plus 5. All of this still over n factorial. So the general term of our Maclaurin series for our function 2x to the fifth e to the x squared is going to be 2 times x to the 2n plus 5 over n factorial. If we wanted to write out several terms of this, we can either evaluate this Maclaurin series for a term formula for n equals 0, 1, 2, 3, etc., or we can take the Maclaurin series for e to the x squared and multiply each term by 2x to the fifth. In either case, our first term becomes 2x to the fifth. Our next term would be 2x to the seventh. The third term would be 2x to the ninth over 2 factorial. And our fourth term would be 2x to the 11th over 3 factorial. And of course, we could continue on with as many terms as we would want, but here is the power series in compact sigma notation for our function f of x, as well as the first 4 terms of the expanded out Maclaurin series. Now that we have our Maclaurin series for our function 2x to the fifth ex to the x squared, we can use this to easily find the values for the 7th derivative of f evaluated at 0 and the 8th derivative of f evaluated at 0. Of course, we could simply take our function and differentiate it 7 and 8 times and then evaluate the resulting derivative with it at 0. However, if you try to do that, you'll notice that the derivatives get very complicated quickly because we have to use both the product and chain rule at each step. So while this is a possible way to answer this problem, it's a very tedious approach, and frankly, using the Maclaurin series, we can get the answers without doing much additional work than what we've already done. The key for this is to realize for the 7th derivative, for example, that c sub 7, the coefficient of the 7th degree term in our Maclaurin series, is given by the 7th derivative of f at 0 divided by 7 factorial. And C7 is the coefficient of x to the 7th in our Maclaurin series, and we see that is equal to 2. That's given to us by writing out several terms of our Maclaurin series, and we only actually need to get to the second non-zero term to find it. And so we know C7 is equal to 2. And so we have 2 is going to equal the 7th derivative of f evaluated at 0 divided by 7 factorial. And so we want the 7th derivative of f at 0, and so we can find that by simply multiplying by 7 factorial. And so this derivative will be given by 2 times 7 factorial, which is a perfectly fine number to use for an answer to something like this. So here, the 7th derivative of f evaluated at 0 is 2 times 7 factorial. To find the 8th derivative of f, we use the analogous formula that C8 is going to be the 8th derivative of f evaluated at 0, all divided by 8 factorial. We then look at our Maclaurin series, and we notice that there is no term x to the 8th in our Maclaurin series. This tells us that c sub 8 is actually going to be 0. And so here we get 0 is going to equal the 8th derivative of f at 0 over 8 factorial. And multiplying both sides by 8 factorial tells us that the 8th derivative of f at 0 is going to be 0. And so here, because there is no x to the 8th term in this Maclaurin series, our coefficient of the x to the 8th term must be 0, and therefore we get the 8th derivative of f at 0 being 0. Notice we could ask the exact same question about any other derivative of our function evaluated at 0. We just need to find the value of the appropriate coefficient in the Maclaurin series and then multiply by the appropriate factorial that's in the denominator. If you'd like to try a similar example on your own, pause the video and find the Maclaurin series for the function f of x equals x to the 10th times sine of x squared. Then use this Maclaurin series to find the value of the 24th derivative of f evaluated at 0. You can resume the video and see the full solution in a few seconds. We start with the Maclaurin series for sine of x, which is the sum from n equals 0 to infinity of negative 1 to the n, times x to the 2n plus 1 over 2n plus 1 factorial, whose first several terms are x minus x cubed over 3 factorial, plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial, and so on. We then substitute x squared in for x in this function, which gives us the function sine x squared with the Maclaurin series n equals 0 to infinity of negative 1 to the n, x to the 4n plus 2 over 2n plus 1 factorial, whose first four terms are x squared minus x to the 6th over 3 factorial, plus x to the 10th over 5 factorial, minus x to the 14th over 7 factorial, and so on. We then multiply this Maclaurin series by x to the 10th to get the Maclaurin series for our function f. So here we multiply our Maclaurin series for sine x squared by x to the 10th. This increases the exponent of x by 10, so that our Maclaurin series now has x to the 4n plus 12 as part of its formula for its terms. And if we work out the first four terms here, we see that those are x to the 12th minus x to the 16th over 3 factorial, plus x to the 20th over 5 factorial, minus x to the 24th over 7 factorial, and so on. We then want to find the value for the 24th derivative of f evaluated at 0. We know that the C24 coefficient, the coefficient of x to the 24th, is going to be that 24th derivative of f at 0 over 24 factorial. And by looking at our Maclaurin series, we can recognize that c sub 24 is going to be the number negative 1 over 7 factorial. It's the coefficient of x to the 24th in that Maclaurin series. And so substituting negative 1 over 7 factorial in for c sub 24, we can solve for the 24th derivative at 0, and it will end up being the number negative 24 factorial over 7 factorial. So that will be the value for our 24th derivative of f at 0. In this example, we're asked to find the indefinite integral of e to the negative x squared dx. Before we evaluate this integral, we should make a couple comments about it. First, it's important to know that there's no elementary form for this indefinite integral. So if we tried to use any basic integration technique to find an antiderivative of e to the negative x squared, we would fail, because there's simply not a function, an elementary function, that can be written as the antiderivative of this function. Maclaurin series, however, gives us a way of writing the antiderivative of e to the negative x squared as a power series, and therefore if we need to do any evaluation, we can do so. The second thing is that this integral doesn't just come out of nowhere, but it's actually important for the study of probability. We don't go into this in this particular video. However, it's useful to know that this particular integral does serve a purpose. So now turning our attention to evaluating the integral, we notice that the integrand has a base of the function e to the x. And so our starting point is going to be the Maclaurin series for e to the x, which is the series from n equals 0 to infinity of x to the n over n factorial. And of course, we can write out the first several terms of that Maclaurin series as 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. And so here we have a Maclaurin series, or the standard Maclaurin series for e to the x. In this case, we don't want to integrate e to the x, we want to integrate e to the negative x squared. And so our first algebraic step is to substitute negative x squared in for x. This gives us a power series from n equals 0 to infinity of negative x squared to the nth power over n factorial. Using properties of exponents here, we can rewrite this series term from this series from n equals 0 to infinity of negative 1 to the n, x to the 2n over n factorial. So we see that we have introduced an alternating sign with the negative 1 to the n. And if we want to write out some of the first several terms here, we can do that. We'll have 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial, and so on. We can find these terms by either just computing this series from n equals 0 to infinity of negative 1 to the n, x to the 2n over n factorial, or by substituting negative x squared in for x in the terms of the Maclaurin series for e to the x. We now have this Maclaurin series for e to the negative x squared, which is the integrand of our integral. And so now we use the term-by-term integration technique to find a Maclaurin series for our elementary antiderivative of e to the negative x squared. So picking up from our Maclaurin series for e to the negative x squared, the indefinite integral of e to the negative x squared dx will be our arbitrary constant c. That will give us all of our antiderivatives for e to the negative x squared. And then we need to antidifferentiate the series term by term. If we look at our series here, the only variable term is the x to the 2n. The negative 1 to the n and n factorial are both constants, so those will remain the same, just continuing to multiply by those. So we have negative 1 to the n times n, all over n factorial. And x to the 2n, we will antidifferentiate that using the power rule, which amounts to adding 1 to the exponent so that we get x to the 2n plus 1. And then we need to divide by that exponent. And so we divide by the number 2n plus 1. And so this gives us a Maclaurin series for our integral. We get our arbitrary constant c plus the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 divided by n factorial times 2n plus 1. Notice that 2n plus 1 and n factorial really don't combine in any kind of nice way, so we really don't have any option except to leave them as is. If we wanted to write out the first several terms of our power series, we could do that. Of course, our first term would be our arbitrary constant c. Our next term would be x. The next term would be negative x cubed over 3, where the 3 is coming from the 2n plus 1, where n is 1. Our next term will be x to the 5th over 2 factorial multiplied by 5, or 5 times 2 factorial if you prefer. The next term would be x to the 7th over 3 factorial times 7. And we could continue on and write out as many terms as we want for this particular Maclaurin series, but here we have our arbitrary constant as well as 4 non-zero terms, x, negative x cubed over 3, positive x to the 5th over 2 factorial times 5, and negative x to the 7th over 3 factorial times 7. If you'd like to try a similar example, you can pause the video and find the indefinite integral of cosine of the square root of x dx. Resume the video and see the full solution in a few seconds. We start with the Maclaurin series for cosine of x, which is the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n over 2n factorial. We substitute square root of x in for x in that Maclaurin series. That gives us an expression involving square root of x to the 2n, which simplifies simply to x to the n. Taking the square root of x and squaring it will give us an x, and then we raise that to the nth power. When we antidifferentiate, that term x to the n becomes x to the n plus 1, and then we need to divide by the constant n plus 1 by the power rule. And so this gives us a Maclaurin series for our indefinite integral of c plus the sum n equals 0 to infinity of negative 1 to the n, x to the n plus 1, divided by 2n factorial times n plus 1. The first several terms of that series would be the arbitrary constant c plus x minus x squared over 2 factorial times 2 plus x cubed over 4 factorial times 3 minus x to the 4th over 6 factorial times 4, and so on. In this example, we want to find the sum of the series from n equals 0 to infinity of negative 1 to the n times 16 to the n plus 2 all over 2n plus 1 factorial. In order to find this sum, we need to do some manipulation with our series term in order to make this look like the term for one of the Maclaurin series that we know. Since the denominator of our term is 2n plus 1 factorial, this makes us think that we want to use the Maclaurin series for sine of x, which we know is the sum from n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. And our series is almost in this particular form, except for the 16 to the n plus 2 is not in the form x to the 2n plus 1. And so what we need to do is we need to write that term in the numerator, 16 to the n plus 2, in the form of x to the 2n plus 1. And we can do this using properties of exponents. So for example, to get started, we might notice that 16 to the n plus 2 can be written as 4 squared to the n plus 2. And this is helpful because this will allow us, when we multiply the exponents together here, to get something to the 2n power. So this would be 4 raised to the 2n plus 4 power. And so now we're very close. Looks like x is going to be 4, and we have 4 to the 2n plus 4. We want 2n plus 1. So we actually have a couple extra 4s. So I can rewrite this as 4 to the 2n plus 1 times 4 cubed. This will break up our term into 4 to the 2n plus 1, which is a term that we want. It has that form that we want, as well as an extra constant here of 4 cubed. So now with this little bit of algebra in hand, we can rewrite our series into something that we can easily compute. So our given series is the sum from n equal 1 to infinity of negative 1 to the n, 16 to the n plus 2 over 2n plus 1 factorial. We can then replace 16 to the n plus 2 with the expression that we just found that it was equal to. So here we have negative 1 to the n times 4 to the 2n plus first power times 4 cubed, all over 2n plus 1 factorial. We can then take this constant of 4 cubed and bring it outside of our summation. Here, every term in our series is going to have a constant factor of 4 cubed, and we can actually bring it outside if we want, and in this case, that will be beneficial to us. And so we're going to have the constant 4 cubed times the series from n equals 0 to infinity of negative 1 to the n, 4 to the 2n plus 1, all over 2n plus 1 factorial. If we now focus our attention on the series here without the constant multiple in front, we notice that this has the exact same form as the Maclaurin series for sine of x with x equal to 4. So if we substitute x equal 4 into the Maclaurin series for sine of x, we will get our series here that we found at the bottom. And therefore, this series is going to equal 4 cubed times the sine of 4. So here we have our exact value for our series. The sum of our series will be 4 cubed sine of 4, which you could also, of course, write as 64 sine of 4 if you wish to have that completely written out. And so the sum of our series will be 64 times the sine of 4. If you'd like to try a similar example, pause the video and find the sum of the series from n equals 0 to infinity of negative 1 to the n, 9 to the n minus 2, all over n factorial. Resume the video, and in a few seconds you'll see the full solution. Since the denominator of our series has the form n factorial, it makes sense to look at the Maclaurin series for e to the x, which has the same property, and that would be the sum from n equals 0 to infinity of x to the n over n factorial, and then to write the numerator, negative 1 to the n times 9 to the n minus 2, in the form x to the n. We can do that by rewriting 9 to the n minus 2 as 9 to the n multiplied by 9 to the negative second power, and then combining the negative 1 to the n and 9 to the n into a single term, negative 9 to the n. We can replace negative 1 to the n times 9 to the n minus 2 with negative 9 to the n times 9 to the negative 2. 9 to the negative 2 is a constant, which we can bring outside our summation, and so we're left with 9 to the negative 2 times the sum from n equals 0 to infinity of negative 9 to the n over n factorial. This summation is the Maclaurin series for e to the x with x equal to negative 9, and so therefore the sum is e to the negative 9. Multiplying that by 9 to the negative second power, which is 1 over 81, we can write the sum of our series as either 1 over 81 times e to the negative 9th, or if you'd like to avoid negative exponents, we can write this as 1 over 81 e to the 9th.